can be performed, right? So would you like to, like, anybody would like to talk about like some of the problems that has been assigned to you, like in particular, um, if I open it up the sheet, right, it maybe the problem, the problem one, which talks about this instruction set and a suitable instruction format and how you can perform it. So I would request, like, like some of you to volunteer and maybe share what you have already done and how you are planning to carry forward this part of the assignment. So do you get time to look at the instruction set which has been provided to you? Anybody?
Yes, sir. Yes, sir.
Okay, so anybody would like to volunteer about the problem one?
Sir, I'd be happy to volunteer.
Okay, Rajat, so can you share your screen and show you what you are planning to show? For?
Yes, sir. Sir, I hope my screen is visible now.
Yes, it's visible. Yes.
Yes, sir. So, me and my partner Neha Dalmia had started working on the first part of the assignment, which was to come up with the whole design. So, first was coming up with the instruction format and the encoding the instructions. So, we actually, after going through the specifications that were given to us about what kinds of instructions we have to use, we decided to divide them up into broadly 6 categories, which is firstly the R format, which is kind of similar to the R format that we have in MIPS, except we don't have the target register here. The target register is by default the RS register. So we have the R format instructions. I format meaning the instructions where we have to add a constant value to the registers. Then we have load and store, and we divided the branching instructions into 3 parts. So basically, B, BL, BCY, and BNCY were instructions in which we only had to jump from jump to a label that was given to us. So we made that as a format. BR was jumping to value stored in a register and address stored in a register. So we made a format for that. And similarly, BLTZ, BZ, and NZ had these instructions had a label as well as a register. So we made a separate opcode for that as well. So that's how we divided our instructions into 6 groups, and then we appropriately gave them encodings in 32 bits for each of the 6 categories. And sir, actually, I had a few doubts as well.
Yeah, please go ahead.
So it's about so for example, there was this instruction BR, and the format was BRRS, would mean that we'll have to go to the value stored at RS.
Go to the RS content. Yes.
Yes. So, sir, is that address is not the offset, right? It's the exact instruction address that we have to go to. Am I right? Or...
Yes, yes. That is to go to the actual offset. Yes.
To go to the actual address that is stored inside the register, right?
Right. Exactly. Yes. Right. So because it gives you it doesn't tell you to add anything, right? I mean, the instruction right. tells you to go to that specific location. So it's okay if you take it as an actual address content, like 32-bit address.
Right. And for B, which was basically
I would also like one thing I would also like to mention is, see, these are all design problems, right? So it also you also have the liberty to make your own assumptions. Okay, so if you prefer to have any other specific base register as your working as your base and you want to add, that is also fine, as long as your interpretation is consistent throughout your design, basically. Okay, so so you can take that as a real, I mean, like an absolute address, and you can do that also. but if you want, you can also consider that as an offset. So that is that flexibility you have as a designer.
have some liberty in terms of that.
Okay.
Right. Okay, sir. So this is basically the different kinds of encoding that we've made, and we've listed that down. Now, our second part was to design the ALU, the architecture of the ALU. So this is how we have designed it. So basically, inside our module, we've not shown the low-level details of how.
One
yes,
second.
sir.
Before we go into that, so you have been able to perform a 32-bit encoding of the entire instruction set, right? Like the entire all the instructions you are able to fit in 32 bits basically, right? So,
yes, sir.
So for your these instructions, like these art type instructions, okay, so can you show the instruction in a format like the suppose you have your like do you have a picture for the entire instruction like which basically captures all possible instructions? This is the format.
So this is the format here. I mean, is this what you're talking about, or?
So when I say 3-bit of for the opcode, right, and RS and 5, okay, so your opcode is suggesting here 3 bits, right?
Yes.
So would you be able to encode all the possible instructions using that? Because
no, sir. We have a function code as well. So our opcode will just signify whether it's R format or I format or B format and things like that. And once we know the opcode is 000, then we look into the function code to differentiate between the various instructions. Like we have 4 bits of function code here.
Okay. Yeah. Okay. So in that case, all the instructions you are able to encode using this. So suppose right tomorrow I want to add any like any other instruction. Okay, so it could be in any of the category. Maybe and like think about like suppose I want to add maybe an arithmetic instruction. So does your opcode have the provision to do that?
Another instruction. Like my opcode can support, opcode will probably be able to support one more instruction because it's 3 bits and I've already used 6 formats. So if a newer format is introduced, I will be able to put only one more.
So this is something that maybe you can think over. Okay. Like this is something that is needed often. Like suppose you like freeze the architecture, make your design and it's done. But it may happen that after that you are interested to add one more arithmetic instruction, right? Or one more logic instruction. So it may happen that you have a better encoding, right, where it is easy to fit in more additional instructions without making any change to the hardware, basically.
Yes. Okay. Understood, sir.
So this is something that maybe you can ponder over.
Yes, and so similarly, let's say if in a particular format, if I want to add more instructions, then I should probably also make this extensibility available in the function code as well.
Right, exactly, yeah. So maybe in that function code, for example, here you have what 4 bits, so you can probably do that here also. Like you have got 4 bits, which means like if you
I can accommodate 5 more.
Yeah,
5 more.
Exactly. So you can probably have some more buffer over there as well. Okay.
Right. Understood.
Yeah. So that's the last line which says that keep in mind while deciding the opcode, you should keep provisions for adding more instructions to the instruction set. Okay.
Sure.
That is the meaning of that. Okay. So now we can go to the second question, which is like identifying the data path elements and drawing the architecture for the arithmetic logic unit.
Yes. So could you give me just one moment? I have to stop my screen share once.
Meanwhile, before he comes back, right? I mean, are there any alternative designs from any group? Like, have other groups have thought something on the same part?
Sir, our group has we are thinking of not using the function code instead of using a longer opcode.
Okay.
6-bit. Should I share my screen, sir?
Of course, share it. I mean, one thing that you have to keep in mind, who is this? Deep, right? Okay, so you have to keep in mind that that when you are, like, I mean, whatever instruction encoding you have, right, will also have a bearance in your decoding complexity. Okay, so think about that also. Like whenever you think about the, I'm encouraging you to think, like something new. That is perfectly okay. But at the same time, when you are making your design for the opcode, right, or in the instruction set format, you also think about what is the consequence of this on the decoding logic. Okay.
Yes,
So
sir.
one of the reasons why, like the typically the RISC designers keep a opcode and a function code separately is to make your decoding extremely simple, because you can, I mean, use the opcode to understand that whether it's an R-type instruction or whether it's an I-type instruction just by seeing the opcode. And you need not think about the decoding logic, right? You need not operate on all the bits simultaneously, but you can work on a small part of the opcode, right? And you can make your decision, right? Otherwise, your circuit can also grow bigger. You see, I mean, so that way, right? I mean, think about the consequence of your coding or encoding on the complexity of the decoding logic. Okay.
Sure, sir. That's one
Yeah.
thing.
Yeah.
So,
Please go ahead.
if my screen is visible,
Yes, your screen is visible. Yeah.
so sir, we have planned two types of instruction formats. One is the I format, and other is the J format.
Mm-hmm.
In the I format, we have so our opcodes are 6 bits long.
Mm-hmm.
I should write it out. So we have 6-bit opcodes, and in the I format, we have a provision for two 5-bit slots. So there may be either register addresses, or for shift statements, the second one can be the shift amount. And a 5-bit shift amount will suffice because we have 32-bit sized words, as well as an immediate for immediate type instructions. And the jump type instruction is for the unconditional jump. So that means branch, branch on branch and link, and the other two, branch on carry and branch on not carry. So for 4 of those, we need the J type instructions, where we need to store the full like the full address, not the PC relative address.
So for your R-type instructions, you keep 6 bits, right?
Yes, sir.
Okay. So the and for your R-type instructions, what is the corresponding opcode? You make it all zeros. Is that so?
No, sir. We have got distinct opcodes for each of the functions. That's what I was saying. Like
Okay.
I did away with the function part.
Okay. So that means you have got like add, comp, and everything.
Yes, sir. Like this part. So 0 0 is add, 0 1 is comp, like this. Although this, I might want to tweak this a bit later if that simplifies it. I haven't actually implemented it, so I can't tell that right now. But roughly, that is my intention: that keeping a distinct opcode for each of the type for each of the instructions.
Okay. So think about or compare, right, it with
Sure, sir. Sure.
with the other alternative, and in terms of the complexity of your decoding logic. Okay. So there you may find a difference actually here.
So I was actually also thinking about the other part, because we are also we needing to create in the input files for actually executing. That means we need to have sort of an assembler. Either we hand assemble it, or write a little program to do the assembling. So like the complexity sort of shifts from the decoding logic to the assembly logic.
So typically, right, I mean, you at this point, you would, yeah, I mean, while you would not like, so you have got your instruction set architecture already ready. So therefore, any code that you take, right, you will be, if you write the corresponding assembly for that, that will be of roughly of the similar complexity, because anyway, these are the instructions that you have, right?
Yes.
What will essentially differ is not is largely on the hardware cost, like like how much amount of resources the hardware, what is your critical path of your decoding, because if
Yes, sir,
there are
definitely.
more delays, then that will affect the performance of your processor basically, right?
Yes, sir. Like in a general case, it would definitely be more beneficial to have a simpler hard decoding logic to
Right.
reduce the critical path. But like
Yeah.
for the interest of this assignment, where we actually have to do all of them in a shorter span. So I was wondering if simplifying so I thought simplifying the design, like simplifying the instruction format might be helpful. That's what I felt.
And also another point that you should keep in mind that suppose you want to add an additional instruction. Okay. So if you freeze the opcode, right, essentially you have got 6 bits and you are, like extinguishing all the opcode, like for identifying the various kinds of instructions, then you may have less liberty to add more instructions.
Should be, I think we can. I'm using 22 of the 64 possible opcodes. So
yeah. So think about the alternative. Like suppose like you have done this in some other way, right? Essentially, which is the standard RISC pattern, for instance. I mean, think about like how many additional instructions you can add vis-a-vis. So it's about your design choice that you are making, right? So if you have got
yes,
two
sir.
design ideas, try to compare between those two figures, like how
Yes,
many
sir.
instructions you can add over there versus how many instructions you can add here. Right?
Yes.
So okay, so I think that is good. So
Shall I
how?
share my screen for the ALU design then?
Okay, yeah, so we can do that.
So before that, there was actually there was something I had to ask. There is this comp instruction here, and over here it says that comp uses both the RS and the RT registers. However, in the meaning, the RT register isn't being used. The 2's complement of RS is just getting.
There is a historic error in it seems actually. So what you can do is you can the argument to the right hand side you can make it RT.
Okay, the argument to the right hand side, that is, we take the 2's complement of RT and store it in RS.
And dump it in RS, yeah.
All right. Okay, sir.
Also, the shift right logical.
Sorry, which one?
The shift right logical is repeated, but it will
Shift
be
right logical,
slightly
yes,
different.
yes. I think this should be
SHRLV,
SHRLV, sir.
Yeah. Okay, yeah.
Yeah.
Yeah, so I think that, yeah, shift right logical, this is okay.
It's repeated, sir.
Yeah, it seems it's repeated. So you can remove one of them probably.
No, sir,
Yeah.
V will be there.
Actually, sir, according to the meaning, this should be SHRLV. Like
Yeah,
the
SHRLV. Yeah. Yeah, so the shift right logical okay with variable.
Yeah, variable.
Yeah. One is a fixed one and the other one is variable actually. Okay.
Yes. Okay,
Yeah,
so
let's discuss the data path then. Right. Okay.
So first was the ALU design then, and after that the shall I open the data path first?
I think it will be good to have the top picture first actually. Okay. That is the what is the bigger picture you design actually. Yeah.
Okay, sir.
Yeah. So this is maybe you can a little bit zoom in.
Is that better? Is it a little better?
Okay, this is good. This is okay.
Yes.
Okay.
Yeah.
So usually, yeah. So you try to explain this. I mean, how you are working, how you are, like making this work. So I will like suggest you to start always with the program counter. That's a good place to start with this description.
Yes. All right. So yes. So the program counter is over here, and the program counter's address is read inside the instruction memory, and from that we fetch the instruction which is 32-bit long, and we pass it into the we have a module called the instruction decoder, which will take in an instruction, and according to its opcode and its function code, it will actually divide it up into um, uh, the register 1, the register 2, RSRT, and if there is an immediate value associated with that instruction, then that gets passed into this immediate line. And also the function code and the opcode that we get from there is passed on to the control logic, which is over here. And basically, so we have just one main control logic, and that control logic takes in the function code and the op code, and on the basis of those, it decides the values that these control lines will be taking. I'll explain what the control lines are standing for in a bit.
So one comment that I have, okay, is this, that is usually, right? I mean, you see, I mean, when you make this design, right, essentially your controller. Okay, so what do you do in the instruction decoder in that case exactly?
Sir, in the instruction decoder, we would, once we get the instruction, we look at the opcode, and then from that opcode, we look at the function codes for that particular opcode, and then see, because the different opcodes have different things to be passed into reg1 and reg2, and for some opcodes reg2 is not there.
Basically, instruction decoder therefore is not doing any computation, right? It is just like breaking out that in
breaking, exactly, yeah, it's doing the breaking up.
There is no logic over there in the instruction decoder.
No, so the logic is present in this control logic.
Okay.
Yes. Shall I continue, sir?
Yeah, please.
Yes. So after the instruction has been broken up in the decoder, what we do is, let's go to the control logic. So the control logic will take in the function code and the opcode, and based upon this table, it will decide what the control lines should be taking as values to facilitate the different instructions based on the opcode and the function code. So for example, if we take the add instruction, so after having passed the after having got the values of all the control lines, for the add instruction, for example, this control line reg dst will be equal to 1 itself, because the destination register for add will be the first register itself, which is rs. So we have this mux which makes the destination register equal to the register rs itself, and res1 and res2, which is rs and rt, get passed into the registers file, and we read the data from them as read data 1 and read data 2. Those two will then go inside the ALU. We have this multiplexer over here for deciding between whether to take the immediate value from this line or to take the register value from this line. Since our add instruction is not an add I instruction, the ALU SRC will set the mux to 0, and we get the RT value here. So the R inputs over here will be RS and RT. Our ALU does the our ALU now chooses the correct operation, which we get from the operation line. Now this operation line will basically be a 4-bit control line as shown over here, and based on the opcode and the function code, we get the appropriate operation from this line. And once this line, this control line goes inside the ALU, the right operation is selected upon getting inside the ALU, and accordingly, there are 4 flags which come out of it, which are basically to handle the branching based on carry, based on sign 0. I think overflow was not needed, so we'll remove that. But carry, 0, and sign were the ones that go inside the branch module and decide whether branching has to be done. For now, for add, this part is not needed. So there is a control line called branch, which will be equal to 0 because no branching is required here. After the required operation has been performed inside the ALU, the result is then carried into the data memory block. I'm sorry, it's not carried into the data memory block because we don't have to read anything from the data memory, or we don't have to write anything to the data memory. So the result is actually just carried to this mux. And since we don't have to do any memory to register writing, this particular control line called mem to reg is equal to 0, which means the result is straight away passed to the registers module here, and whatever the value was inside result gets written into the appropriate write reg that is present here, and our instruction is complete this way.
So you perform a write back, basically.
Yes, we perform a write back.
Okay. So how will you do a branch instruction? Can you just talk about like one?
Yes, absolutely. So, sir, let's take the simplest one first, or let's take the BCY. BCY is taken. So BCY is basically branching when this particular signal carry is equal to 1. So we get the instruction from, we start from the program counter, read the instruction, get the instruction. The instruction decoder now breaks it up into function code, opcode, and we also get the label from here. And the label is directly passed into the branch module. The registers have no value to read, so basically this whole segment over here, including the registers module and the ALU, are basically being bypassed, and they won't be performing anything here. The label goes inside the branch module, and whatever the value. Yes, sir, actually I had this doubt over here as well. So basically in BCY we have been told to branch if carry is equal to 1. So basically, will this be taking the value of carry that was already stored inside carry from the previous summation
Right.
that was
So it
done?
is basically like whenever there is a BCY, right, there has to be sort of, like there has to be a precursor to that. There has to be an instruction
Yes, there
before
has to be a
that.
precursor.
Yeah, and then the BCY.
Got it.
works. Yeah.
Understood, sir. Yeah. So basically, if the carry is 1, and over here, since it's a branch instruction, our control logic will make the branch line equal to 1 as well, and the carry will be 1 here. So and we have the label already. So accordingly, the branch module will then send the appropriate address to the program counter to which it has to jump. From here it goes into the program counter, and then the further thing will happen. We read from that particular address, and then that's what happens.
So yeah, so I think that is pretty good. And so it may so in your branch instruction, when you're handling the branch, right, I mean typically there is also an adder which is needed inside your branch logic. Okay, so keep in mind that when you are designing the branch architecture. Okay,
Sir,
so
actually, what we have done for that part, so basically the adder will be needed in oh, right. We'll need an adder. Yeah. Yes, sir. We'll take that into consideration. Yes.
okay, so this is good, and I think that more or less answers your third question and also the fourth one. So in that case, you are ready for going to the. So note that your controller right here, there is no state, and it's a purely combinatorial design, right?
Correct.
You can implement it as just by some logic signals, right? I mean, some
Yes.
logic gate, basically.
Yes.
Okay. So one thing that I would ask you, all of you, I mean, of course, we will get into the details, is if once you have this top level diagram, like everybody should have this top level diagram, okay? And once you have this top level diagram, it is important for you to break it down. So first of all, like think about that you are writing a Verilog code for the top level where these blocks are present, like it may be maybe the instruction decoding, the branch logic, the memory. Okay, so you should make separate Verilog modules and separate Verilog files ideally for each of these components, and then you are connecting them by wire. So remember that I told about this instantiating by position. So you have got this dot operator to instantiate, right? I mean, I hope you remember that when we talked about Verilog, and you should use that dot operator to instantiate the modules, and then and therefore, right, the top level should be purely structural. Okay, and then you go down to each of these modules and you start developing them. So you see the assignment also has been framed in that way, where the top level has been given this name of kgpdisk.v, and then you have got your internal files actually. So the data path is there, the controller essentially is a separate file, and then you try to like have individual Verilog files for the subcomponents. Okay. So that is I would say like an important thing that if you keep in mind, right, then your design will be modular and you can debug also much easily. Okay, fine. So today I think we have prepared a short tutorial on how to, I think you know most of the parts of how you can write the Verilog program except for the memory, because in your FPGAs or inside your design suite, there is something which is called as the block memory. Okay, so block RAM. So I think Siddhartha, you are there, right? And
Yeah.
Siddhartha will be giving a tutorial on how to use the block RAM. So we'll follow this up. Before we go into that, any other group wants to show their design, and you are most welcome actually to show. Deep Majumdar, you want to show your design?
No, sir, there are a few problems in it yet which you haven't ironed out. So actually quite a few problems. So
Okay.
I'd rather not.
But you get the overall idea, right, about what is to be done?
Yes, sir. Yes, sir. But like I think
Okay.
I've tangled
Okay.
it way too far.
Okay. Any other group wants to show like their opcode design, or you know, like your later data path and other control path, etc.
Yes, like we are group one, me and Animesh, we would like to share it.
Okay, please go ahead.
Yeah. Yes, sir. So, like not much of the opcode, but we would like primarily like to share the data path which we have designed. So, there were
No, actually, Nishad, one thing. I mean, it is important to freeze your opcode at the beginning, because whatever you know, like you design, of course, like maybe there are certain parts which won't change, but there will be a bearance on your opcode on your design complexity.
yeah, sir, it is finalized. Like, if you want, like, I can share it. I just thought that taking time into consideration, I go to the
No,
design
that is
directly.
okay. So are there any? So you already saw like two design approaches in the opcode. So are there any like differences that you would like to highlight, or is your design similar?
Ours uses more bits to like address a operation. So we use 6 for opcode and 6 for function, like similar to MIPS.
Okay.
Others have used much less.
Okay.
So that's so we'll be able to support more number of instructions, but at the cost
Yeah. So
of
one thing,
smaller amount and immediate.
one thing that I would request all of you is in your report, right? When you are submitting, maybe you can add a quantification about how many instructions you can further add. Okay. So that count will be nice for you also to, you know, like keep in perspective about the flexibility of your design. Okay.
Yes.
Yeah.
Yeah. It's like not very different from the ones which Rajat showed before. Yeah, like as Animesh said, the main difference is that we have some extra bits in the opcode and the function code, and like other than that, it's pretty much similar. We have only like three primary types of instructions, and for the branch operations, we are not as such distinguishing between the ones which have a register and which don't have a register to use. Both of them have been integrated in the same one. In the data path, we are taking care of the fact that do we want to branch based on a shift from the reading from a register value, or do we want that to be done using a destination address which has been provided by the user. And other than that, the other two instruction formats are pretty much similar to those which have been discussed. One difference is that we have put some dependence on the opcode as well, instead of merging all the operations having a particular following a particular instruction format into the same type of opcode block. So like what we did was that we found groups of operations which will may in future share a more semantic meaning. So like if we have to add some multiplication or division operations, so they can be added together with opcode 1, and function code we can change accordingly over here. Then for logical operations, we gave it 2, and say more logical operations need to be supported. So we can just modify the function code instead of having a difference in the opcode over here.
Sure.
All the shift type of instructions have one opcode. Immediate types of instructions don't have a dependency on the function code because like we don't have any field for that. So they have been kept separate, and we have put a numbering from behind, like from the higher side of the bits for them. And branch, all the branch instructions have been put together, but in 2 separate blocks. One which require the use of a register and one which have directly do it using a label. So that is the basic opcode design which we have made. Yeah. Coming to the control path. So like yes, like I will start from the program counter only as before. 2 main paths I will like discuss. One is for the arithmetic operations, and the other will be for the branching mechanism, which is like slightly different from the ones discussed before. So like we have a program counter, the instruction memory, the address, like whatever the program counter is pointing to, it will be fetched. So this will be a 32-bit line, and what will happen is that the registers, so this module will take as input the 21st to the 25th bits, the 16th to the 20 bits. So it's fixed that both of these will hold the registers, the destination and the RS and the RT as given in the design, like the document. And we don't need a separate write register because that's the same as the one given before. It will read the data and transfer it to the ALU. For the ALU, we have got some extra inputs. So one is the sign extended 32-bit like I15 to 0 for the immediate types of instructions. One more thing is that we are also passing the shift amount explicitly from this. If it's not an immediate type of instructions, what will happen is that the 11th to the 15th bit, as we have shown over here, this will hold the shift amount value, which will be required in the ALU operations. So we are also explicitly passing that inside our ALU unit. The controller will receive only the opcode. The function codes won't be received by the controller. The function codes will be received by the ALU control. The ALU control, depending on the both of them, what it receives from the controller, the primary controller, and the input it receives from the function code. Combining both of these, it will decide a corresponding select line for the operation which has been performed by the ALU. We also have a design for the ALU, which I will come to later.
Just one comment, sir.
Yes.
The block that you have named as registers, name it as register file. Okay.
Yeah.
This is basically the register file. I think that is the more common name.
Yeah.
Spelling of register is also, you can correct it. Another thing is these are you have denoted the widths of the lines. That is good. But I would also suggest that you know how lines are denoted, if multi-bit buses are denoted, right? So you put a cross, like you cross the
Yes,
line and you write the width beside it. I think
yes,
you should do that because there are so many signals, so many words in the entire design.
Yes.
Just for the sake of readability, I think you should, and different lines have different widths, different buses have different widths, so it will be better if you do that. For very short lines, for example, the input going to the destination and the source register inputs of the register file, those 5-bit inputs, that is fine, that you have already maintained. There you again don't need to show the width, but for the long wires for the students, my suggestion is you add the bus widths. Okay, that would also probably help you to debug if there is any mistake later on.
Yes, sir. Like we'll keep that in mind and make the changes necessary. So like yeah, the ALU control then will select the like whatever the operation it decodes, and
Right.
this is the standard like data memory module. So we have a mux over here as and depending on whether we want to like we want a memory like register we want a memory to register conversion or not. So this mux will select the output of the ALU or the one it has read from the data memory, depending on the control, and pass it on as write data. There is a control for write to destination reg. If this line is on, then the data will be returned to this dest register. Otherwise, it won't be returned.
Right. So how will you implement the register file? Any thoughts on that?
Like we have thought that we can just maintain a 32 cross 32 array for the registers. So it will basically be the each of the like it's a 32 cross 32 array. So each of the 0 to 31 will hold one of the register values, and depending on like more of on a behavioral side, it's very simple, but on a structural side, we haven't thought of it.
Okay. So
we can use an array of D flip flop like flip flops.
Yeah, so I think you can have different, of course, design methodologies, but it is fairly good to have or implement them as registers actually. Okay, and then you have the memory which you are implementing, as we will see in the tutorial today, as a block RAM. Okay, yeah. So this essentially can be implemented in many ways, but and also like remember that they have got two read ports right here in your register file. There are two read ports, right, and one write port.
Yes.
Right. So you can one way to implement that is by using an sort of a multiplexer at the output and to have a decoder at the input, because you need to kind of take the input address, right, and accordingly I mean your input will be required only when you are. So what you can probably do is you can allow, like always some addresses to choose which register you would like to kind of read from. Okay, and I mean for example there can be like two read addresses and one write address, for example, right, in your register file.
Yes, sir. Got it.
So maybe I can yeah, so I can show you one diagram. So maybe if you stop sharing, I can show you one diagram that I have which you can use. Okay.
Yeah, sure. I will stop sharing.
Yeah. So yeah.
Sir, like I also had one specific doubt.
Yeah, just one second. I'm telling to the entire class actually. That is, I hope you can see this, right? This register file diagram, right? Is it visible?
Yes, sir.
Yeah, so you can see here that like these are the different flops that has been implemented, and in the output there are two muxes, and the input there is a decoder. Okay, so the decoder is basically to choose where you want to write, and you can essentially like write into the corresponding flop or the corresponding register, whereas the output, right, essentially can be muxed out from and there can be two parallel muxes, so that you have got two different read paths. So you can choose one address for the read address 0 and have another mux for the read address 1. This is just one possibility, but of course, so what I again suggest is that when you are making the file, right, when you are making these components, again try to draw some diagrams so that you know which are the components, and you can design this in a very modular fashion. So there will be less complexity and your design will be easy to debug also. So this can be one potential way on, and another point I would also like to say is that I think in your diagram, I mean the last diagram which was shown, there is a write enabled explicitly, but the read, right, essentially can be, you can have a read enable, but you can also be optional, because reading is not problematic, but writing, like abruptly will change the content of the register file, right? So the write has to be more carefully handled. Okay. right?
Yes, sir.
So is this architecture understood, right? Okay. So then I think, yeah, so you had a question. Yeah.
I also had one general question from the probably in the assignment. It is not clearly mentioned. Are they expected to have an layer of registers at the input or output? I mean, kind of a redundant layer of registers, because this is a single cycle, but I mean, that is it essential at all? Or
No, I mean, having a register file will suffice actually.
yeah, I mean, yeah, no, yeah, the register file is the internal thing. So I'm
Right.
asking just like a kind of means it is as if it is a single stage of a pipeline with registers on both sides of it. I mean, is that essential or it is not essential?
It is not essential, Rajat. I think we can do
Yeah,
with,
I think that will again create issues with
yeah,
clocks, etc. I think.
yeah. So it will complicate the thing probably. Yeah.
But the register file driving it, they will require a clock or.
No, yeah, so basically, like they don't. I would not suggest to have a clock at this point, but there can be a control over there, like a latch.
Some sort of so then the registers would basically be kind of latch kind of things.
Latch. It can be a
yeah,
it can be a latch based design. So anyway, I think that should be clear once they are into the design. But I think overall there is a clarity. So yeah, so there was another question, right? I mean, from someone. Yeah. So
Yes, sir.
yeah, Nisar got a question. Yeah.
Yeah.
Please go ahead.
So like in the branch instructions where we require to branch on carry, so because like the design is purely combinational, we don't have any data storage other than the registers where we can store values. So what we were thinking is that we explicitly reserve one register for carry, and it will always be in sync like with the last carry which was generated. And whenever the branch module requires, it will read from that register, and then like
typically, Nisarg, I think that the convention is that your adder should have flags. Okay, like it should not have only outputs but also have some set flags. So you can make the carry flag set, and in the next clock cycle you can use that, and that will be used only when there is a specific branch instruction which your branch hardware branch component or whatever, right, branch controller can understand. So
yes,
you don't.
You already have some flags, right? In your design,
yeah, because registers are very, see, these are registers are very precious. Okay, so because they are the fastest form of memory, and although in this case, right, you have got say maybe I don't know like 32 registers or so, but they will be very something that you would typically like to keep it for your programs. Okay, and on the contrary, right, for your flag you just need one bit, right? You don't need, you just need one bit. So why will you waste an entire register for storing a 1-bit data?
like I only had one concern. It's that like because the design is purely combinational, if any of the like the flags are set in the previous operation,
Yes.
but say in the next operation, like when we want to branch, if the ALU also gets some like because we are not explicitly disabling the ALU.
No. So you have to write your program in a correct manner, of course, right? I mean, so if you have got a branch instruction, right, and then there should be like particularly if you are using a branch and carry instruction, then there has to be a previous precursor instruction which basically sets the carry flag.
Yeah. So see,
if you do it, then there won't be any error because
if your branch instruction affects, why should a branch instruction affect the carry output? There is no reason for that, right? So if you correctly implement the logic in the ALU, there is no reason why a branch instruction should affect the carry and destroy it.
Yeah, I mean, so nothing, I mean, it's not that, I mean, if you are bothered about, like that your data gets corrupted, then that will not happen actually. Okay, because your previous, I mean, previously, right, yeah, I mean, of course, like the only problem can happen if there is a previous addition instruction which is not what you expect it to do. Okay, but if you have got a branch and carry instruction and there is a precursor instruction which correctly sets the carry flag, then in the next instruction, when you're executing the next instruction, then it will be correctly interpreted. By the way, like when we are talking about that this is a single cycle instruction unit, it means that every instruction is getting processed in one single clock cycle. Okay, as opposed to when you are doing pipelining, right? You have got a like a flush of instructions which comes one by one in the input. But here the idea is that you are taking one instruction and then you are completing the entire execution of the instruction, and then you are going to the next instruction, right? So the correctness is not affected because of the fact that it is a combinatorial design. Does that answer your concern?
Yes,
So,
sir, I understand.
one thing is, so after suppose the branching happens and it goes to another portion of the code, if further arithmetic instructions happen, then based on the result of that instruction, you are allowed to again reset the carry. So if you perform say another addition or something, okay, in the wherever you have branched to, you perform another arithmetic operation, an addition or whatever, where the carry out result is 0. So then fine, then again the carry out gets updated. That is fine. So your carry out should not remain one forever actually.
But as long as your code is correct with the given instruction set, right, your hardware should give you the correct result. Okay. Fine. So if there are any other batch would like to share their design thoughts? Otherwise, we can go to the tutorial.
One comment. So Nisar, you mentioned that you want to implement the register file with an array of registers where each register itself is 32 bits, right? So this is kind of an two-dimensional array kind of a concept in programming languages. I am not sure that Verilog, at least the version of Verilog that you have been taught and whatever you are using, they directly support two-dimensional memory arrays.
Rather, Verilog will support. There is something which is called as two-dimensional array, but there is a problem with that. Okay, the problem is you cannot simulate actually easily. Okay, so when you are simulating, right, you will not be able to see the content. So therefore, I think
you better just write 32 registers.
The better thing to do is that I showed you one component, right, which I was marked like say one cell of the register file. Okay, so you create a separate module for that and you instantiate it 32 times in your register file. That's the simplest thing to do. Okay.
Understood. Yes, sir.
So one thing that you should keep in mind, I don't know whether you guys use it. There are certain things like generate and all these things just newly come over. But I would advise you for your first level code, don't use those things actually. Okay, use just try to just instantiate it multiple times. Anyway, they are pretty regular in their design, so I don't think it will take you much time to do that actually. Okay, but then you have got better control on the hardware or like the output of your synthesizer. Okay. Okay, so any other group wants to share their design? Okay, 5 seconds. After that, we'll go to something else.
It will be useful to students. I think. See, lot of fine points are coming out in discussions. I think it would help if you have.
Yeah, the fun part about design is you can do anything actually. Okay, so you are flexible, and as long as you can, have an end-to-end thought, you can do anything and you can build your own architecture. Okay, so I think Rajat, we can go to the tutorial in that case. Okay, so Siddhartha, are you there?
Yeah. Yes, sir.
So maybe you can share the screen and you can tell how to instantiate the block RAM. This will be useful to implement your instruction memory as well as your data memory. Okay, in actual processes, we will probably use the cache memory and we will have an SRAM. But here we basically kind of perform this implementation using the BRAM component in your code. And one thing is also important, that in your BRAM, like particularly for the instruction memory, you will, once you write the program and when you're going to test it, remember that the instructions should be loaded into the block RAM. Okay, so you also need to learn how to initialize the block RAM. Okay, so I think Siddhartha will talk about both these things, like how do you instantiate the block RAM and also how you initialize the block RAM component. Okay, Siddhartha, carry on.
Yeah. So, as sir said, like BRAM is generally useful if you use the BRAM as a data memory and an instruction memory. So, there are actually various configurations of a BRAM. So, this is a sample code. Now, first let me show you like how do you actually bring that BRAM module from. So, first, so this is the ISE UI. So, now over here, if you go to this new source wizard, you get something known as IP code generator. So, from this IP code generator, give any name. Suppose this is the name of your BRAM module that you instantiate. Now, over here, this is a generic window that will be displayed whenever you open this IP code generator. Over here, there is something known as this basic elements. Below this basic elements, there is this memory elements thing. Under the memory element category, there is block memory generator. Whenever you go into this block memory generator, you click next, you click finish. A window will pop up. In general, it will take some time, where you get to configure like which configuration of the BRAM you want to use. So this is the block memory generator. Now inside this block memory generator, generally the interface type we choose is native. AXI4 is for a different purpose. Now there are several options, like there is this single port RAM, there is this simple dual port RAM, there is true dual port RAM, there is single port ROM and dual port ROM. Now all these have different purposes. Like if you choose single port RAM, let me show you. Like suppose if you click on next, over here you are having this write width, write depth, read width. In a single port RAM, there is like in this block diagram in the left hand side, you can see like there is an address port, there is a data in port, there is a write enable port, there is clock, and there is a data output. Now you can bring in this enable pin. Now you can see this enable pin got activated. It's actually safe to keep the enable pin. You can also keep it always enabled. So in this single port RAM, what happens is you can write the data onto the BRAM cells or read at a single time. Like you cannot perform read and write at the same time in this single port BRAM. Now suppose if I go into simple dual port RAM, we'll see the difference over here. See, over here there are two address ports, this ADDR A and ADDR B. There are two enable ports. Now there is only one data input and one data output. Like in the first part, like from port A, you can write the data onto the BRAM. From port B, you can read the data from the BRAM. So this is the concept of simple dual port RAM. Now if you use true dual port RAM, you will get more independence with respect to reading and writing. So over here you can see that there are two data inputs, there are two data outputs, and two read enable and write enable ports. So this ENA and ENB actually it enables the enables this part of the BRAM or this port of the BRAM to read and write onto the BRAM memory. Like now there are two ports, but the BRAM itself is a single block. Like suppose if you want to write data onto two blocks of the BRAM at the same time, two different blocks, you can perform that operation by enabling like making this ENA and ENB logic to 1 and WEA and WEB logic to 1. So you can write onto two different parts of the VRAM at the same time. Even you can read from two different parts of the VRAM at the same time by just making this ENA and ENB logic to 1. So this is the functioning of the true dual port RAM. Now suppose this is single port ROM. Now ROM has only been enabled to read, like you can only read from single port ROM, or even if I have this dual port ROM, you can just only read from this part of the block memory. You cannot write anything onto this part of the block memory. Okay, so suppose in general, like for an instruction memory, the instructions are being stored onto the VRAM. You generally do not need to write onto an instruction memory. You, for a data memory, you need to write and read from that. But for an instruction memory, you generally only need to read from that. So for those purpose, this dual port ROM or single port ROM will suffice. So based on whatever you are trying to implement. So this is a basic functioning. So suppose let me give you a demo of this single port ROM. I have already instantiated one single port ROM, no, single port RAM. So over here, just keep this minimum area. Do not change anything in these parts. This write first, read first, and no change actually functions with this dout port. I'll come to that later, like how this write first, read first, and no change actually is functioning. Now over here, the write width as in like each cell of the VRAM, how much data it can accommodate. So and same goes for the read width also. Like the write width and the read width must be same, and the write depth, like how many cells of VRAM do you need. So based on that, like there is something also known as, okay, the register part will be later. So there is something known as this register port. Now beyond the block RAM, like inside the block RAM, there is a register known as the primitive register, and outside the block RAM block, there is another register known as the code register. Now there is an option for pipelining also. So there is a 3-stage pipeline that you can implement using a VRAM, but it gets more complex. Like in order to implement the pipeline, you need to enable these registers, and also there is in order to control those registers, there are specific reset pin also dedicated to those. So those are for higher functionalities. So if you require those things, I can help you with those. Like if you do need to implement pipelining, so it actually helps to achieve a better performance from the VRAM. So you can obviously input those. Now there is another thing known as this memory initialization. Now suppose whenever you instantiate or create a VRAM module, it doesn't have any input, like ideally it should contain all zeros in every cells, but it may contain like certain other values if you define. Like suppose over here, suppose you want to initialize a COE file. Now COE file has some format, like COE is the memory initialization file, what we generally say. So it has a specific format. So suppose I have created an example COE file. So over here you have to, in the first line, you have to write this memory initialization radix equals to 10, or radix as in it can be 2, it can be 10, it can be 16 based on whatever radix you choose. 2 as in binary, 10 as in decimal, and 16 as in hex. And there is this memory initialization vector wherein you can initialize your values. Like suppose you have generated your instructions from some other Python script or anything. You can just fill in the instructions over here. So based on how much memory data write depth or read depth that you have initialized, based on that you can just initialize the memory over here, and this you can load it into over here, and after that just you need to click on generate. Now based on like how much read depth and write depth that we have given, the block memory resource is being allocated. So in general we have chosen over here like 16 should be the write width, 16 should be the read width, and write depth should be 16. Based on that, there are these block RAM resources are separated into 18 KB BRAMs or 36 KB BRAMs. So if you synthesize this or synthesize the design with a 18 KB BRAM, it will show the consumption of 0.5 BRAM. If 36 KB BRAM is being consumed, it will show the consumption of a single BRAM. So over here 0.5 resource is being allocated, and as we are not using any registers as of for this implementation, the latency for read cycle or the write cycle will be just a single clock cycle, and the address width is 4-bit, as we have chosen this 16 as the write depth or the read depth. So this is the address width. So based on this, if you click on generate, you will get this kind of a module over here. So this I have already created from beforehand. So now how do we instantiate in general? So instantiations, so there is, so if you create on this, so if you click on this HDL functional model, you will get a sample instantiation of this BRAM. Like the definitions are being written over here. You do not need to know what the other values are actually for. You just need to use this part. And based on that, I have used this dot convention in order to instantiate a BRAM module. So over here I have this clock, this enable, this write enable, this address, data input and data output. Now this enable signals and the address, those can come from your control module that you have in your code. And in order to test this, like how this actually works, so let me have an initial, I have a basic test bench. So over here, like I do not have any reset signal over here as of now, so do not need it in case of this instantiation of the BRAM. So there is an enable signal, there is a write enable signal, there is this address, and there is data input. And in this BRAM module, so you can actually suppose even if you have instantiated the BRAM, created the BRAM, you can actually modify it. So there is no restriction on like if you want to modify it later. So just double click it, this block memory generator will open, and you can change anything if you require. And see, I have instantiated that memory file, instantiated the block RAM with this memory file. So this memory file that I had shown you earlier. So let's see like whether the block RAM is getting loaded with these values. So this is the basic architecture. So now suppose if I simulate this thing. Just let me expand it a bit. If I change the radix, so in the address I have passed 0, so it should give me like and I have this enable I have set to 1. So ideally in the D output I should get the value of the 0th cell of the BRAM that I have instantiated. So it's giving 1290. So let's see like whether it's correct or not. So suppose I can actually see the memory contents from here. If you go into this test module and then UUT module, and then this mod is the name of the BRAM module. They're going to native over here. There is something known as the memory. Okay, this module. So it's showing in hex by default. Okay, see, the 1290 is the value that was there when I did create the COE file, and it's like I could read the value 1290 based on the address 0. Like if I pass on some different address over here, I can yeah, see, 1477 is the value that was in memory address 1. So this is the value I'm getting. Now suppose you want to write something onto it. So suppose for writing any value, like you need to set the enable port to 1. You need to set this write enable port to 1, and then give the address that wherever you want to write the value, and D in A as in like what is the value that you want to write onto this address. Now based on this, like if I simulate it. Okay. See, now in the D output it's showing 3333. Now this is not the value that you are trying to read from that address. Like over here you can see, like at first, like I was reading some value from address 1, and then I'm trying to write some value on address 10. Now this D output will give you the value that also you are trying to write. So like how this D output functions, that you can actually change from that read first, write first, all those parts. So those actually doesn't affect the functioning of the VRAM, but actually affects the functioning how the what output you want to extract from this D output. Now suppose if you go into what's the content of the VRAM now, as I've written some value already. If I change the radix over here, so okay. See, 333 is being written onto address 10. So this is how the single port VRAM actually functions. So this like the rest of the types of VRAMs that I have, like the variety of VRAM that I've explained earlier. So it functions exactly in a similar way. Like you need to set the values of this ENA, WEA and address and the in to a specified value, to a correct value. It will give you the correct output. So
for example, when you instantiate the block RAM as an instruction memory and data memory, as you can see in the data memory, you need to both read as well as write, right? So like in, for example, in load and stored instructions, so you essentially have got both. You should have both these capabilities, but the instruction memory, when you are implementing, you can initialize it by the COE file. Okay, so so in that case, Siddhartha, did you also show how to write the COE file?
yeah, this is how to write the COE file. I showed.
Yeah, so
yeah.
Yeah, so you can think of that. Suppose you have got your instructions, right? You have essentially these values there, and once you load the COE file, then the instruction memory already have this like pre-written, so you don't need to explicitly write into the instruction memory, but the instruction memory already has the code which will get executed. Okay. So any questions? Any queries on this part, or is it this video will be available so that you can like use this as a reference to practice this part. So any questions from the students? So you see that this is a very this IP generator is a very flexible tool. You can use it and try other variations also, which is left to you at your discretion. Okay, so but this is a very basic tutorial that we provided so that you can get started. So any specific questions? Any thing that you would like to ask? Otherwise, I think we are done. So I see we are done, right? More or less in that case.
Yes, we are done. I think so.
Okay.
So if you have any students, if you face any problem with usage of the IP generator, I think they can probably contact Siddhartha directly.
Yeah,
I mean,
sure.
Hmm.
Sure.
Yeah. So actually, we would prefer you to write your or post your questions in Teams, because then the response
yeah,
can
that
by
will be
others
a
also.
globally. Many students might say have the same problem, and one answer will suffice actually.
Okay. Thank you then, all of you. Hope this is helpful, and we request you to work on this so that we are on time to finish. If you can finish it at the end, you will get a lot of fun to see that your processor is able to like work
So
as your processor. So try to work on the
Friday,
briskly.
yeah. Friday, some more good should groups should give like a description of their design, like
Yeah.
research and other groups. We are expecting some more groups on Friday to have a similar to have made similar progress as Nisarg's group.
Yeah. So only Friday. Normally we we'll start at 2 o'clock.
Yeah, we can start at 2.
Because 4 o'clock there is some event in the department actually. So
Oh yes. Yeah. So I think by 4 we'll finish. Like today also we are finishing. So on Friday at least some more groups, if you give describe the spec, maybe few more questions would come up. There will be more clarifications, and that will benefit everybody actually.
Yeah.
And those groups who have not yet made similar level of progress, please hurry up, okay? Because this semester will finish, as we said, the lab is going to finish on 12th, and this submission deadline is 13th. As per institute rules, labs should finish by 12th. We cannot extend it any further. Okay.
And this is actually all said and done. This is actually a very easy assignment. Actually,
This is an easy assignment. It's a combinational
systematically,
circuit
if we
design.
approach it, then it should be done actually. So
Mostly combinational circuit design assignment. Other than the register file and the memory modules, they have some enable signals, but other than that, it's pure combinational design. Okay, this you should be able to do. I mean, it shouldn't be too much difficulty.
I mean, if you work at the problem all at once, it may look a bit complicated. But if you break it up and do it, then like it should be much manageable. So try to therefore do it systematically and regularly. I'm pretty sure most of you will be able to finish it in time.
And already a suggested organization into different modules has already been given in your assignment sheet. If you look, right? So if you follow that, it should not be that difficult. I mean, this is a large circuit, no doubt, but some of the assignments you have solved previously, they were more complicated than this. So you have been able to successfully solve this means this you would also be able to solve this quite easily. You have to be patient, and most importantly for large designs, you have to be systematic. Don't keep everything for the last moment. Everything will become hodgepodge. Okay. So 2% teams, you distribute the work that, okay, three modules will be designed by one person, 3 modules will be designed by another person, and then you together integrate it.
Yeah, and ensure that both of you are participating. That is also important.
Yes, one person doing and the other person taking it easy is not good.
Okay, thank you then. Bye.
Okay, I just want to make another announcement related to the theory course. So some of the the theory grading of exam 2 is going on. For some of those answer scripts which have been graded, their marks have been uploaded on Google Sheet or maybe Moodle, but not all have been graded till now. The TAs are working on it. So please please be patient and keep your questions, because I have received emails. Students have said that why were marks deducted? Comments are not visible. Comments will be made visible. Why marks were deducted, etc. So please be a little patient. Okay. By the end of this week, hopefully by this Sunday, we will have everything graded for exam 2. Okay. So please be a little patient.
Bye.
Okay. Thank you. ঠিক আছে তাহলে I think we can wrap up for today. Bye.